Okay, let's get started. We are usually here to take a really broad look at a topic, pull from all kinds of different sources, and, find the most interesting story. But today is different. Today we have a very, very specific mission, a high-stakes one.
We do indeed. And it's a mission I have to say that I really enjoy because we're going right back to the absolute foundations of what we do. We're not just, browsing the literature today.
Whoa.
We are deep in the foundational texts.
Miller, Guyton, Morgan, and Mikhail.
The ICU book, David Chambers. The core stuff.
Exactly. Today, we're simulating an exam prep session. This is specifically for you if you're that learner persona getting ready for the Gujarat University MD Anesthesiology exams. So the books are open, highlighters are out. I'll be playing the role of the postgraduate student. I've done the reading, but I need to get the delivery just right for the exam. And you, this is your home turf.
I will be your senior MD anesthesia faculty member, your external examiner, if you like. And I'll warn you now, I am going to be very particular about definitions. In the exam, especially in the Viva, precision is everything.
I'm ready.
You can know the concept inside and out, but if you use loose language, you lose marks. Simple as that.
I am ready for the grilling. Our topic today is, well, it's the absolute bread and butter of our trade. Oxygen transport, the oxyhemoglobin dissociation curve, I'll probably just call it the ODC, and of course, carbon dioxide transport.
And you really can't overstate how important this is. It's impossible. You simply cannot be an anesthetist if you don't get, on a fundamental level, how oxygen gets from the flow meter on the machine all the way to the mitochondria.
And how the exhaust fumes, the CO2, get back out.
Exactly. This comes up all the time. It'll be a 10, maybe 20-mark long question in your theory papers. It's a staple in the Viva, and you'll see it in OSCEs. Interpret this ABG, or the one everyone dreads, draw the curve from memory.
That's the goal, then, to go beyond just the basic physiology and get into those examiner-approved explanations and the clinical side of things. So let's do it. We'll break this down, starting with Part B, oxygen transport.
Okay, so imagine we're at the table. It's the Viva. I lean forward and I ask you, Doctor, describe the forms in which oxygen is transported in the blood. Where do you begin?
I'd start by stating very clearly that oxygen is transported in two distinct physical pools. First, oxygen that's bound to hemoglobin, or Hb, and second, the oxygen that is dissolved directly in the plasma.
Good. You've established the two pools. Now, don't wait for me to ask the next question. Immediately quantify their contributions.
Right. Straight to the number. The contributions are, well, they're vastly different. The hemoglobin-bound oxygen carries the overwhelming majority. We're talking something like 97 to 99% of the total.
And the other part?
The dissolved fraction is biologically tiny in comparison. It's only about 1 to 3%.
Okay, tiny is a word I'd avoid in an exam. It sounds a bit vague. Let's drill down. What law governs that dissolved fraction?
The dissolved oxygen follows Henry's law.
Which states?
Which states that the amount of a gas that dissolves in a liquid is directly proportional to its partial pressure.
Good. And for oxygen, what is the solubility coefficient? This is a number you just have to know.
It's 0.003.
The units. Be precise.
Ah, right. It's 0.0003 milliliters of oxygen per deciliter of blood per millimeter of mercury of partial pressure.
Yes, 0.003 ml/dl mmHg. So let's make that real. If we have a normal arterial oxygen tension, a PaO2 of, say, 100 mmHg, how much dissolved oxygen is there actually?
Okay, so you just multiply 100 by 0.0003. That gives you 0.3. So 0.3 milliliters of oxygen in every 100 milliliter of blood.
Exactly, 0.3. Now, let's put that in perspective. Compare it to the oxygen bound to hemoglobin. Let's say you have a normal hemoglobin of 15 grams per deciliter. Roughly how much oxygen is carried there?
No, fully saturated, that would be around 20 milliliters of oxygen per deciliter.
So there you have it.
So we're comparing 20 milli, which is the bound fraction, against just 0.3 millimole, the dissolved part.
Which is precisely why both Guyton and Miller make the point that hemoglobin increases our oxygen transport capacity by 30 to 100 times. Without hemoglobin, our cardiac output would have to be impossibly high. Your heart would literally explode trying to pump enough blood to keep your brain alive.
That leads us perfectly into the next big exam question. This is exam goal for sure. The definition and equation for the oxygen content of blood.
The CaO2 equation. This is non-negotiable. You must be able to write it down from memory flawlessly. Walk me through it.
Okay. CaO2 equals, open bracket, the hemoglobin concentration in grams per deciliter, multiplied by 1.34, multiplied by the arterial saturation, SaO2.
Close bracket.
You're done?
Plus the dissolved part. So open bracket, 0.003 multiplied by the PaO2, close bracket.
Perfect. Now let's pick at the numbers because an examiner will. Why 1.34? What is that number?
That's Höfner's constant. It's the oxygen combining capacity of hemoglobin. So how many ml of oxygen combine to 1 gram of hemoglobin? But here's the Viva trap. If you do the math based on the molecular weight of hemoglobin, the theoretical maximum capacity is actually 1.39 milliliters per gram. So why do we, as clinicians, use 1.34?
Right. Miller and the ICU book are very clear on this. The 1.39 number is for, like, a perfect pure hemoglobin molecule in a lab. But in vivo, in a real person, you always have a small amount of dyshemoglobins.
This is.
Things like methemoglobin or carboxyhemoglobin, they are forms of hemoglobin that just can't carry oxygen.
So 1.34 is the clinically relevant, the corrected value.
Exactly. It accounts for that small non-functional fraction.
Good. So in an exam, if you write 1.39, you must immediately qualify it as the theoretical max. If you just write 1.34, you're safe. Now, why does this whole distinction between saturation, the SO2, and content, the CaO2, matter so much to us in anesthesia?
Because they tell you two very different things, and it's dangerous to confuse them. Saturation is just a percentage. It tells you how full the tank is. But content tells you the actual volume of fuel in the tank. You'd have a patient with 100% saturation, their tank is completely full, but if they're severely anemic, maybe with a hemoglobin of 5,
A very common scenario.
then their tank is the size of a thimble. Their actual oxygen content, their CaO2, is critically low, even with a perfect sat.
Excellent. That is the key point. The pulse oximeter might look fantastic reading 100%, but the tissues are starving. Anemia reduces the capacity of the system.
It reduces the size of the tank, even if the tank is full to the brim.
Never confuse the two. This leads us directly to oxygen delivery, or DO2. What's the formula for that?
Oxygen delivery, which is also called flux, is just the cardiac output multiplied by the oxygen content. So DO2 equals CO times CaO2. And then there's a factor of 10 in there.
Why the 10?
That's just a conversion factor to get the units right, to go from deciliters, which is what CaO2 is in, to liters for the cardiac output.
Correct. So based on that equation, what are the 3 pillars of oxygen delivery? If you're in the ICU, your patient is in septic shock, you need to improve their tissue oxygenation. What are the 3 levers you can actually pull?
Okay, so lever 1 is the hemoglobin concentration. I can give a blood transfusion.
Good.
Lever 2 is the cardiac output. I can give IV fluids or inotropes to improve blood flow.
Right.
And lever 3 is the arterial oxygen saturation. I can increase the FiO2 or add PEEP to get more oxygen onto the hemoglobin that's there.
And of those 3, which ones usually give you the most bang for your buck?
Well, usually it's the cardiac output and the hemoglobin, like what we just calculated. The dissolved fraction, which is driven by Pa2, is pretty negligible. Cranking the FiO2 to get the PO2 from 100 up to 400 doesn't do a whole lot for total delivery compared to, say, fixing an HB of 7.
Exactly right. I think there's a graph in the ICU book that shows this very clearly. It compares the effect of anemia versus hypoxemia.
I remember that one. A drop in hemoglobin from 15 to 10 has a much, much bigger impact on oxygen content than letting the saturation drop from 100 to 90%.
A much more drastic effect.
Yeah.
And this brings us to a really key concept for critical care, which is the idea of critical DO2.
Okay.
Normally, in a healthy person, our oxygen delivery far exceeds our consumption. Our metabolism is what we call supply independent. But in shock states, if delivery drops below a certain threshold, the critical DO2 consumption suddenly comes dependent on supply.
And that's when things go bad.
That's when aerobic metabolism fails, anaerobic metabolism kicks in, and the lactate starts to climb. That's the definition of shock, really.
Okay, I think I've got a handle on the transport basics, so now let's move to the part that everyone dreads having to draw in an exam. Part C, the oxyhemoglobin dissociation curve.
The ODC. Let's start simple. Describe its shape to me.
It's a sigmoid curve. It's S-shaped.
Why? Why isn't it just a straight line, like the relationship for dissolved oxygen? What's the underlying mechanism?
It's all because of the hemoglobin protein itself. The mechanism is called cooperative binding, or sometimes heme interaction.
Explain that. Imagine you're explaining it to a first-year resident. What is actually happening at the molecular level?
Okay, so the hemoglobin molecule, it has 4 heme chains. When it's totally deoxygenated, no oxygen on it, it exists in what's called the tense state. The T state.
10.
It's physically rigid. There are these salt bridges holding the structure really tight, and they kind of cover up the binding sites. This makes it really difficult for the very first oxygen molecule to force its way in and bind. And that difficulty is why the bottom part of the curve is so flat. It has a low affinity for that first molecule.
Good. So it's hard to get started. What happens next?
But once that first oxygen molecule manages to wedge its way in, it breaks those salt bridges. It's like a key in a lock. It causes this big conformational change that snaps the whole molecule into the relaxed or R state.
And this R state.
It exposes the other three binding sites. It makes it much, much easier for the second, third, and fourth oxygen molecules to jump on board. I think it's David Chambers who says the fourth molecule binds something like 300 times more easily than the first one did.
A fantastic description of the biochemistry. Now give me the examiner-oriented physiological explanation. Why is the sigmoid shape so brilliant from a design perspective?
Well, it gives us two really distinct functional zones. The upper flat part of the curve, that's the safety zone.
And where does that part of the curve operate?
In the lungs, where we're loading oxygen. Because it's flat, it means that even if our alveolar partial pressure of oxygen drops a bit, maybe from high altitude or some mild lung disease, our saturation stays really high. You can drop your PO2 from 100 down to, say, 70 mmHg, and you're still over 90% saturated. It's a great buffer.
A safety margin. Good.
Yeah.
And the steep part of the curve?
That's the unloading zone. This is what's happening down at the tissue level, where the PO2 is around 40 mmHg. Because the slope is so steep there, a very small drop in the local partial pressure results in a massive offloading of oxygen from the hemoglobin.
It dumps its cargo.
Exactly. It lets the hemoglobin dump a huge amount of oxygen right where it's needed most without needing a huge pressure gradient.
Excellent. Now, to anchor this curve, to give it a specific reference point, we use the P50 value. Define it for me.
The P50 is the partial pressure of oxygen, the PO2, at which hemoglobin is exactly 50% saturated.
And what's the normal value for a healthy adult?
It's 26.6 millimeters of mercury.
Good. Or in kilopascals?
About 3.5 kPa.
No both. But mmHg is more common in vivas. So why do we care so much about this one point on the curve? What is its clinical significance?
It serves as the standard measure for the position of the entire curve. It tells us about hemoglobin's affinity for oxygen.
Explain that.
If the P50 increases, say, to 30, it means you need more oxygen pressure to get to 50% saturation. That means the affinity has gone down. That's a right shift. And if the P50 decreases, say, to 22, it means affinity has gone up. That's a left shift.
Perfect. This is exam gold territory now. The shifts of the curve. Let's start with the right shift. What causes it?
I always use the mnemonic CADET face right.
Okay, break it down for me.
C is for increased CO2. A is for acidosis, so increased hydrogen ions or decreased pH.
Good.
D is for DPG, which is 2,3-diphosphoglycerate. E is for exercise, and T is for increased temperature.
A very good mnemonic.
Yeah.
Now, you're a postgrad, so you need to explain the mechanism. Let's take acidosis and CO2. What is the Bohr effect?
The Bohr effect specifically describes how carbon dioxide and hydrogen ions reduce hemoglobin's affinity for oxygen. Mechanistically, the high concentration of hydrogen ions, the protons, they bind to specific amino acid residues on the hemoglobin protein. I think it's the histidine residue.
Yes, that's correct. And what does that binding do to the molecule?
That binding stabilizes the T state, the tense, deoxygenated state.
That is the key phrase you must use. It stabilizes the T state. By keeping the molecule tense, it actively forces it to release its oxygen.
And from a physiological standpoint, that makes perfect sense.
How so?
Think about a tissue that's metabolically active, a muscle during exercise, or an organ that's ischemic. It's hot, it's acidic from lactic acid, and it's pumping out CO2. Those are the exact CADET conditions.
Exactly. The red blood cell arrives, it senses this local environment, and thanks to the Bohr effect and the high temperature, it dumps extra oxygen right there. It enhances unloading where it's most needed.
It's a beautiful feedback loop.
It is. Now, what about 2,3-DPG? What's its role?
2,33-diphosphoglycerate. It's an organic phosphate that's made inside the red blood cell during glycolysis. It's a byproduct.
And how does it work?
It binds specifically to the beta chains of deoxyhemoglobin. It sits right in the central cavity of the molecule, and it acts like a physical wedge. It prevents the hemoglobin from snapping back into that high affinity R state. So again, just like acid, it stabilizes the T state and promotes oxygen release.
Very well explained. Now let's flip it. Let's talk about the left shift. What causes the curve to move left? Increasing affinity.
Well, basically the opposites of CADET. So decreased temperature hypothermia, decreased CO2, which is alkalosis, decreased 2-Fab3-DPG. And then you have the special cases,
Yep, sure.
fetal hemoglobin, HbF, and carboxyhemoglobin, which you get from carbon monoxide poisoning.
Let's use a clinical scenario. You're in the ICU. You have a post-cardiac surgery patient who is intentionally made hypothermic. and you've maybe been a bit overzealous with the ventilator, and you've hyperventilated them, so they're now alkalotic. Why is that combination so dangerous for tissue oxygenation?
Because both of those things, the hypothermia and the alkalosis, cause a significant left shift of the curve, meaning the affinity of hemoglobin for oxygen goes way up. The hemoglobin latches onto the oxygen and just won't let go. It's too sticky. So even if your pulse oximeter reads 100%, the hemoglobin isn't releasing that oxygen at the tissues. The bonds are too strong.
But so you can have
profound cellular hypoxia with a rising lactate, despite a perfect saturation reading.
Yes, that is a classic Viva trap. Doctor, the sats are 100%, the blood pressure is fine. Why is the lactate 8? The answer is often a left shift preventing unloading. We sometimes call it high-affinity hypoxia.
Right, and what about stored blood? That's another classic example.
Tell me about it.
Well, the 2003 DPG inside stored red blood cells gets depleted over time. After about a week or two in the blood bank, there's hardly any left. So if you do a massive transfusion with old blood, you're essentially giving the patient a huge load of left-shifted hemoglobin.
And how long does it take for the body to fix that?
It takes up to 24 hours for those transfused cells to regenerate their 2-pol-3 DPG stores. So for that first day, oxygen delivery to the tissues from that transfused blood is impaired.
Correct. And very briefly, fetal hemoglobin. Why does it have a left-shifted curve?
Because the fetus has to be able to steal oxygen from the mother's circulation across the placenta. So by definition, fetal hemoglobin needs to have a higher affinity for oxygen than maternal adult hemoglobin.
And what's the structural reason for that?
Structurally, HbF has gamma chains instead of beta chains. And these gamma chains just don't bind 2-vel-3-DPG very well. So without that 2-vel-3-DPG wedge keeping it in the T state, HbF naturally prefers the high-affinity R state.
Excellent. And the last one, carbon monoxide. This one is particularly bad.
Yeah, it's a double whammy. It's really nasty.
Explain the two mechanisms.
Okay, so first, it binds to the same site as oxygen on the heme molecule, but with an affinity that's 200 to 250 times stronger. So it just outcompetes oxygen and reduces the number of available binding sites. That's like a functional anemia.
That's the first hit. What's the second?
The second hit is that when a CO molecule binds to just 1 or 2 of the 4 sites on a hemoglobin molecule, it causes a conformational change in the remaining sites. It forces them into a super high affinity state.
So what does that do to the curve?
It shifts it massively to the left, and it also changes the shape from sigmoid to more of a hyperbola. So whatever little oxygen is still on that hemoglobin molecule is now locked on. It absolutely will not be released to the tissues.
Perfect. And remember, to diagnose that, you can't use a pulse oximeter. You need a co-oximeter.
Right, because a standard pulse oximeter just sees a red-colored molecule and thinks it's oxygenated. It'll give you a falsely high, maybe even 100% saturation reading.
Very important point.
Okay.
Okay, let's move on. Part D, carbon dioxide transport. This is often the neglected topic compared to oxygen, but for us in anesthesia, we are constantly manipulating CO2. So how is CO2 carried in the blood?
It's carried in 3 main forms.
Yeah?
First, as dissolved CO2, just like oxygen. Second, and this is the main one, as bicarbonate, HCO3-. And third, as Carbamino compounds, where it's bound directly to proteins.
Good. Now give me the numbers. What are the relative contributions of those 3?
Okay, so the dissolved CO2 is about 7%. CO2 is much more soluble than oxygen, about 20 times more so. The dissolved fraction is a bit bigger than for O2, but still pretty minor.
Okay.
The vast majority, about 70%, is carried as bicarbonate.
70%.
And the remaining 23% or so is bound to hemoglobin and other plasma proteins as those Carbamino compounds.
Correct. The major textbooks like Guyton and Morgan all agree on those figures, more or less.
Yeah.
Now, you said bicarbonate is the main form. Explain the mechanism of its formation.
Yeah.
This involves the red blood cell, right?
Yes, the red blood cell is like a little factory for this. CO2 diffuses from the tissues into the plasma and then quickly into the RBC. And inside the RBC is the key enzyme,
Which is
carbonic anhydrase.
the crucial catalyst. What does it do?
It takes 1 molecule of CO2 and 1 of water and rapidly catalyzes their conversion into carbonic acid, H2CO3. This reaction is super slow in plasma, but lightning fast inside the RBC because of the enzyme. Then this carbonic acid is unstable and it instantly dissociates into a hydrogen ion, an H+, and a bicarbonate ion, HCO3-.
Okay, so now you've produced all this bicarbonate inside the red cell, but you said it's the primary transport form in the plasma.
Yeah.
So how does it get out?
It gets actively transported out. There's an antiporter protein in the red blood cell membrane. It pumps 1 bicarbonate ion out into the plasma. But to maintain electrical neutrality, because you're moving a negative charge out, you have to move a negative charge in.
And that negative charge is?
Chloride. A chloride ion, Ki-, shifts into the RBC from the plasma.
And we call this?
The chloride shift, or the Hamburger phenomenon.
Good. Now what happens to that other product, the hydrogen ion, that's left behind inside the cell? You can't just let acid build up.
No, it gets buffered, and this is a really important point. It gets buffered by the hemoglobin molecule itself. Specifically, deoxygenated hemoglobin, or reduced HB, is a much better buffer for protons than oxygenated hemoglobin is. It soaks up that H+ ion, binding it to histidine residues.
An excellent point that links everything together. We talked about the Bohr effect earlier. Now let's talk about its counterpart, the Haldane effect.
Okay, so the Haldane effect is kind of the other side of the coin. Bohr is about how CO2 affects oxygen affinity. Haldane is about how oxygen affects CO2 carrying capacity.
Give me the formal definition.
Deoxygenated blood can carry more carbon dioxide than oxygenated blood.
And the mechanism. Why is that?
It's for two main reasons, and they both happen in the lungs when we take up oxygen. First, when oxygen binds to hemoglobin, the molecule changes to the R state and becomes a stronger acid.
And as a stronger acid,
it has to release the hydrogen ions it was buffering. Those protons are kicked off. They immediately combine with bicarbonate reformed carbonic acid, which then becomes CO2 and water, and we exhale the CO2.
That's the first reason. And the second?
The second reason is that oxygen binding also directly destabilizes the Carbamino compounds. It shakes the CO2 loose from its binding site on the globin protein.
Excellent. So to summarize, in the lungs, the act of oxygenation actively promotes CO2 release. And in the tissues, the act of deoxygenation promotes CO2 pickup.
It's a perfectly efficient system for gas exchange.
It is. Okay, let's move to part E and integrate these concepts. In an exam, you need to be able to contrast the Bohr and Haldane effects instantly. Give it to me.
Okay. Bohr effect. This happens at the tissues. High CO2 and high acid cause oxygen to be released. It's all about facilitating unloading.
And Haldane.
Haldane effect. This happens mainly at the lungs. High oxygen causes CO2 to be released. It's about facilitating gas exchange and getting rid of waste. A good mnemonic I heard is that Bohr starts with B, which is like breathing out oxygen into the tissues. And Haldane starts with H for holding on to CO2 in the venous blood.
If that works for you, use it.
Yep.
Now, let's talk anesthetic implications. We are constantly fiddling with these variables. What is the relationship between alveolar ventilation and PaCO2?
It's a rectangular hyperbola, meaning they are inversely proportional. If you double your alveolar ventilation, you will have your PaCO2. If you have your ventilation, your PaCO2 will double. It's a very predictable relationship.
And what's a key difference between the CO2 and O2 curves?
The CO2 curve doesn't have a saturation point like the ODC. In the physiological range, it's pretty much a straight line. You can just keep loading more and more CO2 into the blood as the pressure rises.
Good. Now, what about permissive hypercapnia? This is a strategy we use in ARDS. We use low tidal volumes to protect the lungs, and we accept that the PaCO2 might rise to 60 or 70 mmHg. Is there a potential side benefit to that in terms of oxygen delivery?
Yes, there is. We're tolerating that respiratory acidosis because through the Bohr effect, that high CO2 and low pH will cause a right shift in the ODC.
Which helps too.
Which helps to unload whatever oxygen we do manage to get into the blood. So in a severely hypoxic ARBS patient, that little bit of acidosis from the hypercapnia might actually improve tissue oxygenation.
Correct. It's a physiological trade-off we make. Okay, one more special situation. High altitude. This is a great example of competing mechanisms. Walk me through it.
Right. So you go up to high altitude. The inspired PO2 is low. This stimulates your peripheral chemoreceptors, and your first response is to hyperventilate.
And what does that do?
Step 1, hyperventilation blows off CO2, causing a respiratory alkalosis. Step 2, that alkalosis causes a left shift of the ODC. This actually helps you load the scarce oxygen in the lungs, which is initially a good thing.
Good.
But that same left shift now impairs oxygen unloading at the tissue, so it's a mixed bag. That's bad.
So how does the body acclimatize and fix this problem over the next few days?
Over a few days, the chronic hypoxia acts as a stimulus for the red blood cells to produce more 2,3,3-DPG. Step 3, that increase in 2,3-DPG pushes the curve back to the right, counteracting the left shift from the alkalosis. This restores our ability to unload oxygen at the tissues. It's a beautiful dynamic balance.
Exactly. Well explained. Now, before we finish, the most practical part, Part F, exam integration. The Viva. I am the examiner. I hand you a clean sheet of paper and a pen. I say, Doctor, draw the oxyhemoglobin dissociation curve. What do you do?
The first thing I do is not panic. And I don't just scratch out a random S shape, I construct it properly.
Oh.
First, I draw the axis. The x-axis is PO2 in millimeters of mercury. The y-axis is SO2 in percent. I label them clearly.
Crucial. Go on.
Then I mark 3 key specific points on the graph before I draw the line.
What are they?
Point A is the normal arterial point. PO2 of about 100 mmHg corresponds to a saturation of about 97%. Point B is the mixed venous point. PaO2 of 40 mmHg corresponds to a sat of 75%, and point C is the P50. PaO2 of 26.6 mmHg corresponds to a sat of 50%.
And then?
Only then do I connect those 3 points with a smooth sigmoid curve, making sure the top part is flat and the part between the venous and P50 points is steep.
If you do that, you will pass that question. If you just draw a wavy line, or you forget to label the axis, or you miss the P50, you fail it. It's that black and white.
And I'd probably also add dotted lines to show the shifts. A dotted line to the right labeled acidosis fever, and one to the left labeled alkalosis hypothermia.
Excellent. Now, what if you're asked for a table comparing oxygen and CO2 transport?
Okay, key differences. Solubility. CO2 is 20 times more soluble. Primary transport form. O2 is almost all on Hb. CO2 is mostly bicarbonate.
Good.
Curve shape. O2 is sigmoid due to cooperative binding. CO2 is more or less linear, no saturation. And the interaction. Bohr effect for O2, Haldane effect for CO2.
Perfect. And finally, let's revisit that classic Viva trap we talked about. I look at the monitor and say, the patient's sat is 100%, but their Hb is 5. Is the patient hypoxic?
My answer has to be precise. I must first distinguish between hypoxemia and hypoxia.
Define them.
Hypoxemia is low oxygen in the blood, specifically a low PaO2. Hypoxia is low oxygen at the tissue level, which is a failure of oxygen utilization. So that patient with an Hb of 5 is profoundly hypoxic anemic hypoxia, even though they are not hypoxemic. Their PO2 is fine, their saturation is fine, but their oxygen content is dangerously low.
An absolutely critical distinction. Okay,
right.
let's wrap this up. Give me the high-yield summary for the exam, the key take-home points.
1. Oxygen is carried 97% on hemoglobin. You have to know the content equation. 1.34 times Hb times sats, plus the dissolved bit. 2. The curve is sigmoid because of cooperative binding, that T to R state transition. 3. P50 is 26.6 mmHg. It's the anchor point that defines the curve's position and affinity.
Well, good.
4. Right shift is caused by CADET and helps unloading at the tissues. Left shift helps loading in the lungs, but can be dangerous.
Yeah.
5. Bohr effect is for the tissues, helping O2 release. Haldane effect is for the lungs, helping CO2 release. 6. CO2 is mainly carried as bicarbonate, about 70%, and this process relies on carbonic anhydrase and the chloride shift. And 7, and this is maybe the most important, always distinguish between oxygen content, the CO2, and oxygen saturation, the SaO2.
That is an excellent summary. If you can articulate those points as clearly as you just did, you will do very, very well. Now, I want to leave you with one final provocative thought. Something to think about that goes a little beyond the textbook. We spent our entire careers in critical care obsessed with oxygen delivery, the DO2. We push it with fluids, with blood, with inotropes. But sometimes, especially in sepsis, you can have a patient with a high cardiac output, a high DO2, and their lactate is still climbing.
Right.
This is the concept of cytopathic hypoxia. The problem isn't the delivery anymore. The problem is that the mitochondria, the engines of the cells, are themselves broken. No amount of fuel delivery will fix a broken engine. It really challenges our whole philosophy. Is our obsession with achieving supernormal oxygen delivery actually helpful, or could it even be harmful?
That's a huge question, a fascinating rabbit hole for another deep dive, I think. Okay, for you listening, here's your homework. Practice drawing that curve, seriously. Right now, after this is over, grab a piece of paper, a napkin, anything. If you can draw it from memory, label the axes, and mark the 3 key points, you are halfway to mastering this topic.
Absolutely. It is the secret weapon for the Viva.
Oh.
Good luck in your preparations.
Thanks for joining us for this deep dive. We'll see you next time.